Howdy. The purpose of this video is to walk through the proofs of some of the trigonometric identities. In particular, we're going to take a look at the even-odd identity. And after that, we're going to prove the law of sines, which is used for triangle solving, and the law of cosines, which is also used for triangle solving. When we consider the even-odd properties, we're going to begin with a unit circle and start by measuring an angle theta from due east. And so here's our angle theta. And we would like to investigate the even and odd behavior of sine of x and cosine of x. Recall that a function is even if it satisfies f of negative theta is the same as f of theta for all theta. And a function is considered odd if f of negative theta equals the opposite of f of theta for all theta. So what we need to do to test even and odd behavior is to construct the angle negative theta. And we're going to do that by reflecting the angle theta about the x-axis. At least we will if we can get the angle theta to behave, which is not doing curl. Come on. You silly angle. Yeah, it's unbelievable. All right, well, let's try this again. We will put the angle back. You get moved, get flipped, and now you get put back. Huh. How about that? It really doesn't want to move. Hey, gotcha. Okay. Well, sometimes that's the way it goes. Now, here's the thing. If we now consider x and y coordinates where these intersect, then you can see that the x and y coordinates are cosine theta and sine theta, and by definition, the x and y coordinates here are cosine negative theta and sine negative theta. Now, what I claim is that the cosine of negative theta is exactly equal to the cosine of theta. And the proof for that is very simple. Because these two angles are congruent, theta and negative theta, and because the hypotenuse of each of these is 1, therefore by hypotenuse angle, these two triangles are congruent, and therefore the length right here, which is the x-coordinate, cosine theta, has to be equal. And the y-coordinate right here is going to be equal but opposite to sine theta above. And therefore we have cosine of negative theta is equal to cosine theta, which means cosine is even. And sine of negative theta is equal to negative sine theta, which means that sine is odd. Once we have these two results, we can generate results for the other 4 trig functions fairly easily with the negative angle test. So for example, if I want to investigate the odd-even behavior of tangent, then I can rewrite tangent as tangent of negative theta as sine of negative theta over cosine negative theta. Now using my even and odd properties, I can rewrite that as negative sine theta over cosine theta, which is obviously negative tan theta. In other words, tangent is an odd function as well. the exact same proof. I should say a very similar proof. It shows us that cotangent is also an odd function. See if you can make some predictions about secant and cosecant, even or odd, and then prove those predictions. Pause the recording for just a moment, take a moment to prove those predictions, and here we are again. You should have found that secant is even and cosecant is odd. And so there we have it. We have 1, 2 even trig functions, and 1, 2, 3, 4 odd trig functions. Well, we're going to move on to the laws of sines and cosines. And I am going to begin with a way of expressing a right triangle in terms of its hypotenuse and angle. Suppose I have a right triangle. There's a right triangle right here. And the information that I know about it is the hypotenuse, which I'm going to call h, and one of the angles, which I'm going to call theta. I can now represent all of the other sides in terms of theta using sines and cosines. In particular, this side is going to be h sine theta, and this side is going to be h cosine theta. And the reason for that is fairly simple. If I draw a corresponding triangle in the unit circle with the same angle theta right here, and this hypotenuse is 1, and this point is cosine theta sine theta, which means the length of this leg is sine theta, and the length of that leg is cosine theta. And if I now expand this triangle by a scale factor of h, so that its hypotenuse is now h, then that's going to expand all of the legs proportionally. So we're going to call this the right triangle representation. And it leads us to a very important lemma called the area lemma. A lemma is a little mini theorem that helps us prove other theorems. And so the area lemma is going to go like this. If I take some triangle, I have a generic triangle, so let me make one. If I take some triangle and I label its sides A, B, and C, and the corresponding angles across as capital A, B, and C, the area of triangle ABC is given by 1/2 of the product of two sides AB times the sine of the included angle C. Now, why is this lemma true? It's fairly simple. We know already that the area of a triangle is 1/2 base times height. So I'm going to drop a perpendicular from B and call this H. Drop H perpendicular to side B from point B. And you may remember from geometry that it's always possible to do that. Okay? Now, having done this, the area is immediately equal to 1/2 base times height. So that's easy enough. But what is H? Well, if we go back to our right triangle representation, we have a right triangle here with a hypotenuse of A and an angle of C. So H is immediately equal to A times the sine of C. And if I use commutative property to rearrange, then I have the result, just like that. This is very useful in its own right. I often use the area limit in solving geometrical problems. And in particular, we're going to now use this to immediately prove the law of sines. The law of sines is also going to take a random triangle. And we're going to want the sides A, B, and C. And the corresponding angles opposite them is capital A, capital B, and capital C. And now I claim that the sine of angle A divided by the length of A is equal to the sine of angle B divided by the length of B is equal to the sine of angle C divided by the length of C. And the proof is really, really delightfully simple. The big idea of the proof is area. So if I were to remember the law of sines in one word, the proof goes area. And here's how we do it. We're going to take our area lemma and we're going to apply it to the same triangle 3 times using a different included angle each time. Let's start with angle A. If I use A as the included angle, and the sides that include it are B and C, and so the area is equal to 1/2 BC sine angle A. If I use B as the included angle, then the two sides that include it are A and C, and so the area is also equal to 1/2 AC sine B. And finally, if I use C as the included angle, then the sides included are A and B, and so the area is 1/2 AB sine C. Now, because A, B, and C are all sides of the triangle, they can never be 0, so it is legitimate to take this equality and divide through by 1/2 ABC, which is guaranteed to not ever be 0. And when we do that, then all sorts of delightful carnage occurs, and what we end up with is the law of sines. Sine A over A equals sine B over B equals sine C over C. This law of sines is very, very useful with obtuse triangles, triangles that have an obtuse angle. It will sometimes give spurious results, so you have to be careful about that. Finally, let's consider the law of cosines. The law of cosines is the extended Pythagorean theorem, or the generalized. If we take any triangle and mark it up just as we did the previous triangle, with sides A, B, and C, at angles opposite, capital A, capital B, capital C, then the law of cosines states that the square of side C is equal to A squared plus B squared minus 2 times the product of AB cosine of the included angle C. A squared plus B squared minus 2AB cosine of the angle between. Now, the proof for this actually appeals to the Pythagorean theorem twice. We're going to drop ourselves a perpendicular, and we'll call it H right here, from point B, just as we did previously. And when we do, we're going to mark this part right here as X, And this part right here is therefore b minus x. Take just a moment to think about that. H divides b into two quantities, x and b minus x. And now we're going to apply the Pythagorean theorem to the two right triangles that were created by the perpendicular. Here and here. Okay. So, when I apply the Pythagorean theorem, let me write what we've done. Drop perpendicular h from b. If I apply the Pythagorean theorem to the green triangle, then I get a squared is equal to h squared plus x squared. And if I apply to the red triangle, then I get c squared is equal to h squared plus the quantity b minus x squared. Now this could use a little bit of algebraic simplification. So we're going to do h squared plus b squared minus 2bx plus x squared. And that gives us an expression for c squared. Now what we're trying to do is to solve for c squared right here. And so we now look for opportunities to substitute or eliminate. And what we notice is that the h squared and x squared are both present right here. And so that suggests that maybe we want to subtract the top one from the bottom one so that we get c squared minus a squared is equal to, bam, bam, these go away, b squared minus 2bx. Okay? Again, solving for c squared. And this is a perfectly good expression, but x was a creature of our own creating, and it is the leg of this right triangle. So we're going to use the right triangle representation and say that x is the same as the hypotenuse A times the cosine of the angle C. Check that. X equals A cosine C. And now we can substitute to get c squared is equal to a squared plus b squared minus 2ab cosine of the angle between. So where does this leave us? Well, there are two things that I want you to carry away from this. First are the actual laws themselves. And the second thing that I want you to observe is the methods of proof that we use. First, with regard to even and odd, we use the test of plugging in negative data. And then with regard to the law of sines, we used area as a proof technique. And with regard to the law of cosines, we used the Pythagorean theorem as a proof technique. What should you do in response to this video? You should turn off the video and explain to yourself the proofs of the law of sines and the law of cosines. If you can explain them to yourselves, then you have mastered those proofs.